maybe I should say in the beginning that I went through the program of the masterclass, and it's pretty intense. It's filled with analysis of partial differential equations, and it's quite a lot of material to digest. So I decided to give you a break, to give the students a break in particular, and do some lighthearted stuff. And in particular, what I want to show you is, I'm not going to go into any analysis or numerical computations or something like that. I just want to show you what you can do with partial differential equations and what partial differential equations can do for us. And when I say I want to show you, then I mean with a twist. And the twist is that I want to illustrate things with pictures, with photographic images. And actually, they're my pictures. I'm a photographer also. And well, if you don't enjoy the partial differential equations that you're going to see, I hope you will at least enjoy the pictures. So this is really the material that I've collected in a book, which has been quite a while ago, in the year 2006 to be precise. The book has appeared with Springer. It's called Applied Partial Differential Equations: A Visual Approach, and I'm working on the second edition now, and it should hopefully be out in more or less short time. I'm just trying to get rid of this green tab, but I cannot. Okay. Anyway, what are partial differential equations? Well, partial differential equations relate certain state variables like mass, velocity, energy to their variations with respect to some other variables like space or time, typically. And partial differential equations are based and rooted in differential and integral calculus, which was invented by Leibniz and Newton back in the 18th century. And since then, partial differential equations have had quite a career. They were used by many physicists like Euler, actually mathematicians, I should say physicists and mathematicians, like Euler, Maxwell, Boltzmann, Navier, Stokes, Einstein, Brandt, Schrödinger, Pauli, Dirac, Turing, and then finally, and then recently, more or less recently also, in economics by Black and Scholes. And I could actually name many more examples of important scientists who have used partial differential equations to describe the phenomena that they were interested in. And actually, partial differential equations provide an important modeling tool for the physical sciences, for theoretical chemistry, for biology, for the social sciences, and for the engineering sciences. And now comes a very important point. The nice thing about partial differential equations is that they are very accessible to numerical simulations. I mean, clearly, it takes a lot of numerical analysis and computational understanding to solve complicated nonlinear partial differential equations, but there is always an inroad to the numerics. So that is something very nice. Now, partial differential equations actually govern many phenomena occurring in nature around us and also in the socio-economic behavior of, say, human populations, also of animal populations. Partial differential equations are completely indispensable today for advancing engineering and technology. And finally, and this is a very important point for me, and I'm sure for many of us here, partial differential equations involve deep and beautiful mathematics. And actually, I should say that in my picture of the scientific world, of the applied mathematics world, deep and beautiful mathematics and important applications go hand in hand. They are by no means separated, or even some people say that one excludes the other. I do not feel that way. The way I feel is that they really go hand in hand. Okay, so now here is a list of topics that I want to go through today. I'm not going to manage to speak about all of them in the time that I have, but let me just give you the list here. So I'm going to start out with gas dynamics, in particular with the Boltzmann equation. Then I'm going to pass over to fluid and gas, to the transition fluid gas dynamics, Navier-Stokes-Euler equations. I'm going to speak about the kinetic modeling of granular flows, chemotaxis and formation of biological patterns, semiconductor modeling, free boundaries and interfaces, reaction diffusion equations. Then, if I make it until there, as far as there, Kantorovich optimal transportation theory, wave equations, digital image processing, and socioeconomic modeling. So this is a list of topics that at least you can find in the book. I don't really know where I'm going to. I think I have half an hour or something. So I'll see how far it takes me. And as I said, I will show you these topics, or illustrate you these topics through, let's say, the vision of a photographer and a mathematician combined. Okay, so let me start out with the Boltzmann equation of gas dynamics. So what you see here is a particular cloud formation over the plains of Patagonia. The cloud has a name, which you can, the cloud system here has a name, which you can find here. Well, I mean, it's something that you see quite often, but I'm not sure whether you have asked yourself, what are the equations? What's the mathematics behind that? How can you model cloud formation? And here is a way, here is a way of going about it that is through the Boltzmann equation. Now, the Boltzmann equation is a very, very complicated nonlinear, highly non-local partial differential equation. It's an equation for a phase space density F, which describes the motion of the gas under consideration. Typically, you have a force field acting on your gas, and then here you see on the left-hand side you have partial derivatives, and I'm not going to read to you what is here because as I said, it's a very complicated equation. I'm not really expecting that you understand the equation. At this point, I just want to give you a feeling for what it is. On the right-hand side, you have a very, very non-local operator, and this equation was actually set up by, you could say, by two important physicists, more or less at the same time. One of them was Maxwell, James Clerk Maxwell, and the other one was Ludwig Boltzmann. They basically wrote that equation and they were the first to understand the concept of entropy, which is deeply related to the particular structure of this equation. Now here, as I said, I'm interested in clouds. There is a certain modification of the Boltzmann equation which allows you to model clouds, and that is, you pass from the Boltzmann equation to the so-called stochastic coalescence equation, where you describe, which is an equation for the density of mass droplets in the gas, which are sort of resolved in the gas. So you can think of clouds as unions of small droplets of water, which are somehow dispersed in the air. And here you would see another non-linear, non-local equation, which is very much derived from the famous Boltzmann equation, and which sort of models directly the motion of clouds. As I said, the main application of the Boltzmann equation is macroscopic cloud modeling. There is very related approaches, for example, through lattice Boltzmann equations, which you can think of as space discretized version of discrete velocity collisional kinetic equations. And the interesting thing, or the nice thing about lattice Boltzmann equation, is there is a very nice way of proving the convergence to the solutions of the fluid mechanics Navier-Stokes equation in a certain scaling limit. And those lattice-Boltzmann equations can also describe cloud, motion, wind, smoke, aerosols, even pheromone kinetics, and they are able to represent very complicated geometries, phase transitions, and chemical reactions involved. Now, macroscopic fluid equations, as I said, they can be derived from Boltzmann type equations, and they are typically used to describe the interaction of air with cloud particles like bigger water droplets, ice crystals, aerosols, non-volatile ones on a macroscopic basis, of course. Big difficulty here is, of course, the vapor-water droplet formation phase transition. This is really the crux of the story. So what I want to show you here is some pictures of clouds. Here you see so-called cumulus fractus clouds, which approached the volcano Cotopaxi in Ecuador. This was actually a very spectacular scene. In the lower picture, you see the cloud as it sort of, actually in the upper picture, you see the cloud as it starts to come in, and then like 3 or 4 minutes later, it already looked like that. And like after 5 minutes, the cloud basically covered the mountain. Here you see another picture of very different clouds, cirrus flocus and cumulus clouds over the Cuernos del Paine in Patagonia. Another cloud formulation over the Torres del Paine in Patagonia. And that's basically what you can do with the Boltzmann equation. Okay, here's an interesting thing. I talked about kinetic equations, Boltzmann equation, and macroscopic equations, Euler, Navier-Stokes. So at some point you start to ask yourself, what is the transition from, how can you describe the transition from the kinetic regime to the macroscopic regime? And here is a very good example. Think of the space shuttle. The space shuttle that was used maybe 20 years ago. And think of in particular, think of the re-entry phase of the space shuttle. So when the space shuttle, first of all, is in outer space, the flight is completely ballistic, meaning described essentially by the trajectory equation, okay, by the ordinary differential system, essentially Newtonian law. Then when the space shuttle starts to enter the atmosphere more and more, at some point, there will be a dynamic balance of the collisions of the shuttle hull with the air particles. And that already happens in the upper atmosphere, sort of in the first part of the re-entry phase. And that is precisely the regime that is described by the kinetic Boltzmann equation. Now, finally, when the space shuttle gets closer to the Earth, at some point you will have a very small mean free path flow that is in the lower atmosphere. So, and then this is where the macroscopic regime hits. So you basically have here a case of a transition from collisionless ballistic to collisional kinetic Boltzmann modeling to macroscopic fluid dynamics. And all those 3 types of models have to be used, and actually were used in practice when describing the re-entry phase, the very complex re-entry phase of the space shuttle. Now, another example is aircraft design. And in particular, if you speak to aircraft engineers, they will tell you that the most complicated part in designing is, of course, the wing. And this is a typical task for experimental and computational fluid dynamics. Typically, what people use is incompressible Euler and Navier-Stokes equations, depending on the specific application that you have in mind. And sometimes people use lattice Boltzmann simulations. That has actually been done recently, in particular when turbulence modeling is in the range of interest. So here you see an airplane close to Rio de Janeiro, something that we always see. And here is an image of which for me as a Viennese is very important. This is the bust of the Austrian physicist Ludwig Boltzmann, who is buried, whose grave is at the Central Cemetery in Vienna. And what you see on his tombstone is an engraving of the entropy formula. And yeah, and Boltzmann, as I said, he was really at the origin of all this jointly, and no, I shouldn't say jointly, I should say independently with James Clerk Maxwell. So the way it happened really was that Maxwell wrote the Boltzmann equation down for the first time. So he wrote the equation actually in a weak form, which is very interesting. At that time, there was no theory, no weak theory, no theory of weak formulations, but Maxwell already did it. And then Boltzmann was the one who understood the entropy concept behind it. Okay, that brings me to Navier-Stokes equations, and of course the Euler equations of fluid and gas dynamics. And what you see here is a waterfall. It's a picture of a waterfall on the Brazil-Argentina border. And assume that for some reason you are interested in modeling waterfalls. You are interested in modeling, or more generally, the motion of rivers. And then you will, of course, have to resort to the Navier-Stokes and Euler equations. So here you see the incompressible Navier-Stokes equation. So basically, it is a system of, say, in 3 dimensions of 3 highly nonlinear, very complex differential equations for the fluid velocity vector. And another variable that enters here is the pressure, is the fluid pressure, which is determined by this incompressibility constraint here. Now, for those of you who have ambitions in terms of science and in terms of money, if you prove the global in time existence of smooth solutions of that system of equations, the Clay Foundation will give you $1 million. And I'm sure if you happen to be under 40, you will also get a Fields Medal. Okay, so a classical application for this is in hydrology, when you sort of when you reduce the Navier-Stokes equation to the so-called Sarvenant system, which is then able of modeling the motion of rivers. And the basic variable that is in the game here is this function h, which you can think of as the water height over the bottom. And you have to think of here as, well, I mean, the boundary of the fluid is of course a free boundary here. And the Sarvenant system essentially has the shape of a compressible P system with quadratic pressure law and external forcing. That's actually very interesting, although it models an incompressible phenomenon. Okay, so here let me show you a few more nice pictures. Iguazu Falls from, I think this was from the Brazilian side. Here is more, and here is pretty much a wilder waterfall in South Africa, but also those can be very successfully modeled with the equations that I have shown you. Okay, when you talk about fluids, you also have to talk about turbulence, of course. Now, turbulent flows are characterized by apparently chaotic, random changes of velocities, and you have vorticity appearing, and now it becomes very, now it is very important to say that vorticities appear on a huge variety of scales. And all this occurs at sufficiently large Reynolds numbers. Non-turbulent flows are called laminar. They are represented essentially by streamline flows, where different layers of the fluid are not disturbed by scale interactions. Okay. Now, when you simulate turbulent flows, you are entering a very, very complex and computationally expensive area, because small and large scales in the solutions of the Navier-Stokes equations have to be resolved at the same time. They always interact. So you have scale interactions at all levels. Okay. Now there are simplification attempts which are based on time averaging of the Navier-Stokes equations and using empirical closure conditions for the correlations of the velocity fluctuations, but that is maybe too much detail here. So here you see a typical turbulent flow in a waterfall, right? I mean, there is no way that you can get around by sort of describing this by a laminar type of simulation. Yeah, so, and what you see here is very interesting. You see a turbulent flow up there on the upper part of the waterfall. You see an almost laminar flow on the lower part, and here you see a transition region. So again, here you have to basically deal with interaction of all kinds of scales, from very, very small scales, maybe in the region of millimeters up to the scale of meters. Okay. Granular material flows. Now, when you think of granular material and when you live in Saudi Arabia, the first granular material that comes in your mind, of course, is sand, because here we are really surrounded by a lot of sand. And then when you go out into the desert, you see very strange formations and patterns which are created by the sand in conjunction with, say, the wind and the weather and so on. So the question is, how can you model this? And again, there is a kinetic description for granular flows in terms of energy dissipating particle collisions. And essentially, what you can write down here is a Boltzmann-Enskog equation for inelastic hard spheres, which is the best representation for granular media that I know of. So again, you have a Boltzmann type equation for the phase space density of the material of the flow. The left-hand side is again a differential terms which describe the free motion, and here you have the collisional integral which describes the interaction of the granular particles. From a kinetic equation is always associated to a macroscopic scaling limit, and when you do the macroscopic scaling limit here, you get this complicated system of fluid type equations, where here you have basically the left-hand side is classical Euler, is a compressible Euler, and here you have a right-hand side in the temperature equation, which corresponds to the temperature relaxation, which is a basic feature of granular media. Again, a very complicated differential. So when you want to describe sand dunes, of which we have many in Saudi Arabia, of course, right? Then this would be the equation that you have to resort to. And here you see a very high dune. I think it's one of the highest in the world. It has a name. It has actually a number. It's dune 45, and you find it in the desert of Sossusvlei in Namibia. It's probably close to 300 meters high or something. Here you see complicated dune shape, right? I mean, it's almost a circle which is broken up in one spot here. This, of course, comes through the interaction of the sand that forms the dune with the weather, with wind profiles and so on. Right? So here you see a ridge, the ridge of a sand dune. Now you can ask yourself, well, why is this dune relatively stable, right? And so why doesn't it sort of collapse into something flat, or locally flat? So why do you have some kind of almost singularity in the profile? And again, all this you can find out by just looking at these equations. Again, complicated dune fields, and here you see you are on very different scales. Okay, so if you want to describe fields of dunes, then you will have to move to very different scaling very complicated scaling limits of the Enskog equation. Here's another, which I think is an interesting picture of a dune field. And here what you see is the ridge of a dune, which on one side is pretty flat. On the other side, there is this structure here, right? You see this ripple structure. And actually, it turns out that the equations that I've shown you, they admit a very huge variety of stable stationary states. And that is why you can find a lot of very different, or seemingly very different patterns in sand dunes. Yeah, here is another, if you want, granular pattern equilibrium state. And this is a picture of a Zen garden in Kyoto in Japan. Again, the principle is the same. Granular material is put into a certain shape, right? And the shape remains stable. Of course, I mean, trivial to say, you cannot do this with fluids in general. You can only do it with granular materials. So here you have an interesting phenomenon. When you think of the modeling of the growth, of the collapse and the stability of piles of granular material, then this can actually be done in the context of the Markowich mass transportation theory, using P. Laplace equations. There is actually a very interesting lecture notes collection by Craig Evans, where you find precisely the computation for this problem, that is for the stability and the possible collapse of piles of granular materials. Yeah, and it actually turns out that at a certain angle, you have stability, and if you and if this angle is, or if the angle of attack is larger than this one, then you basically get collapse. Rita, how much time do I have left? Very little, right?
Well, let's say 5 minutes.
Okay. Okay, now I want to show you another example application, that is chemotactic cell motion and biological patterns. So, I mean, you've all seen a zebra, right? And you might have wondered, I mean, how is this pattern in a zebra formed? I mean, what happens? I mean, what's the mechanism behind it? And it turns out that this is extremely related to the so-called Keller-Segal model for chemotaxis and the resulting Turing instability phenomenon. So what is Turing instability? Well, think of a system of two reaction diffusion equations, where you have to think of U as an activator substance, you have to think of V as a deactivator substance, and the important thing here is that the diffusivities in these two equations are very different. Say here diffusivity is 1, and here diffusivity is, say, very, very small. Yeah. Now, actually, yeah, and assume that the origin is a stationary state of the associated ODE system, meaning that when you cancel the Laplace operators here, you have a stable, steady state of the ODE system at the origin. Now, you would think that when you add diffusion, stability might only be enhanced. But this is really not the case. Actually, Turing has shown that if you add diffusion with very different coefficients, then what you basically gain is unstable modes in the linearized Fourier picture. Okay, so that means adding diffusion is not always a good thing. And precisely this phenomenon gives rise to the pattern formation that I've shown you on animal skins. Okay. And turns out that biologists have actually been after finding the activators and deactivators for various animal skins, and they have found some of them. So I mean, this is modeling. Turing modeling is a sort of here very, very close to the biological reality. Giraffes, exactly the same thing, just very different patterns, which again you have to think of as a result of the instability of wide ranges of diffusivity, caused by wide ranges of diffusivities. You have a kudu coat, same thing. Zebras. Actually, and if you realize, of course, not two zebras are never the same. So there is a huge range of possible patterns that you can get out of the model. Crocodiles, yeah, crocodiles, actually it turns out that the skin formation of crocodiles is a chemotaxis phenomenon that can be modeled by the Keller-Siegel system. Turtle shells, exactly the same thing. So what's the control mechanism that forms the turtle shell? Again, this is governed by chemotaxis, meaning there is a certain substance which the turtle produces, which sort of tells the correct cells that then eventually form the shell to migrate to the specific locations. Okay, yeah, I think I've done a few topics. I think I stop here. And I thank you very much for the attention. If you're interested in the rest, you find it all in the book. And hopefully in the second edition, which should come out next year. Thank you very much for your attention.
Thank you, Peter. Thank you for this very cynic view of the partial differential equations. So the time for questions and answers starts now. And we already have a question in our Q&A. And it goes like, if the line structure that we can see, for example, in the dunes in the Death Valley is related to laminar flow.
Okay, that is an interesting question, because laminar flow is really defined for fluids. So it's basically laminar flows basically means the motion of streamlines, yeah. And here in the dunes, what you really have is, of course, a granular flow, which I would not define as laminar. Yeah. I mean, certainly, if you think of it, the line structure is clearly caused by a wind which blows into one specific direction. So then there is no interaction of directions here. But I would still not call it a laminar phenomenon.
Thank you. More questions?
Peter, I definitely would like to buy the book after your talk. Should I wait for the second edition?
Please. You can be the first buyer of the second edition.
So it's coming out this year? You said next year?
Yeah, I hope. Well, yeah.
I don't know if I can wait.
Thank you. You're very kind.
So for those of you, people are going to hate me, but I think we have this book available online in the library. So if you are at KAUST or if you join KAUST, you will be able to see this book in our library, and then you can buy it.
Okay, and then we can buy the second edition. Okay, very good.
And the advantage of being at KAUST, you can always have autographed book, right? So.
Well, but talking about our library system is very good. We should really say that.
Yeah, this is.
More questions?
There's a request in the Q&A.
Ah, sorry. If you can briefly show the other photos.
I can. So here, so this is the next chapter would be on semiconductor modeling. So here there's a few macro shots of semiconductors, but the mathematics behind it is actually a drift diffusion Poisson system, which describes the motion of electrical charges in the semiconductor. Again, no time to go into that, but that is really very much related to the chemotaxis system that I've shown you. It's just that in the chemotaxis system, you model attractive forces, and here you model repulsive charges. And these are pictures that now we all have seen, and the world has moved on. There is more integration, of course, going on now. And so I just want to show you a few macro shots. Okay, now this is interesting. Free boundary problems, phase transitions. Iceberg. So you ask yourself, you have an iceberg and you're interested in describing the interface. That is the boundary where the iceberg hits the fixed water surface. And the mathematical problem behind is essentially a single phase Stefan problem, which can be used for iceberg modeling. And it's a classical case of a free boundary problem where the unknown is not only a function, but is also a geometric object, right? That is the free boundary. Okay, and here you see a few icebergs. And those are really spectacular ones. And here you see a picture of the Stefan boundary, which lies now under the water surface. Okay, or the part of the Stefan boundary that lies under the water surface. You see that you can have very, very complicated geometry in free boundaries, of course, right? Glacier modeling, glacier modeling. Yeah, I don't want to go into the piece. So you ask yourself, how do those geometric structures come about, right? And what are the equations that you can use to model them? Or how does the glacier flow? Yeah? And how can you describe the boundary of the glacier with the rocks? And you can also, and here is some pictures of reaction which illustrate reaction diffusion equations. What you see here is rice paddies, and I have no time to go into explaining why this is a reaction diffusion equation, but believe me, if you want to model African savanna, for example, again, predator-prey models. I mean, we all know that in African savannas, you have a lot of predators and you have a lot of prey. And the question is, how do they equilibrate, and how can you describe that? Predator-prey, which is essentially an example of a reaction diffusion system. And here you have, oops, sorry, just as a more or less a joke, here you have a classical predator-prey interaction, right? Okay, here you see, and our Brazilian friends will know what this is, right? This is the Lagoa in Rio de Janeiro, and if you're interested in modeling the ecology of lagoons, again, you can set up certain reaction diffusion equations, and I think our friend George Zubelli has particularly worked on this. Optimal mass transportation is something that I really like a lot. I have not much time to speak about it. The interesting thing is it was basically initiated by a French civil engineer, Gaspard Monge, who had to transport construction material from the place where it was located to the construction site. And he asked the question, how can I do this in an optimal way, right? And this then led to all kinds of mathematical problems which go into measure theory, into nonlinear partial differential, highly nonlinear, I should say, partial differential equations like the Monge-Ampere equation and so on. And I have And well, more or less the same principle applies if you ask yourself, how does a river flow in the landscape? And how does it branch in the landscape? Again, this can be modeled by optimal mass transportation. Branching of vessels in lotus leaves, same thing. I'll just show you some pictures. Well, no, I don't want to show you more because then you are not going to look at the book, maybe. Okay.